Chapter 13. Electric Wave Telegraphy by Resonant Circuits. A simple radiating circuit like that shown in Figure 60 of the preceding chapter, consisting of a spark gap with one side grounded and the other attached to an antenna, has a definite period of electric oscillation. The receiving circuit has also a characteristic period of oscillation. A maximum effect will be obtained when the two have the same fundamental period, that is to say, when the two circuits are in resonance. Marconi recognized this fact, and in his specifications, particularly with reference to the use of a receiving resonator of two metallic vanes, he provides a method of experimentally determining the size of the vanes that will give resonance with the transmitter. In the course of further experiments, it was soon found, however, that the type of simple receiving conductor in which the coherer is inserted directly in the antenna circuit is not a very discriminating resonator. Also, it is usually not practicable to change the size of the vanes or the length of the vertical wires in order to make changes in the period of the circuit. When several wireless telegraph stations are to be operated at once, it is highly desirable, in order to be able to avoid confusion, to have a method of readily adjusting the receiving circuit to resonance with the wavelengths it is desired to receive, and out of resonance with undesired signals of a different wavelength. Several methods have been devised for accomplishing this result, which, though attaining only limited success, have yet been of great advantage in wireless telegraphy. Circuits capable of being attuned or adjusted for resonance are called syntonic circuits or resonant circuits. In the present chapter, it is proposed to discuss some of the general types of resonant circuits. Quantitative experiments in regard to resonance and the record of the practical details of construction of apparatus will be given later. A simple variable circuit. A simple method of easily varying the period of a receiving circuit consists in the use of a variable inductance, shown in Figure 62. This is inserted between the detector and the antenna, or between the detector and the ground at the receiving station. Such a variable inductance, or tuning coil, is made of a single layer of wire wound on an insulating tube of glass or ebonite, and is varied by a contact sliding along the coil so as to put more or fewer turns of inductance into the circuit. A similar tuning coil, though usually of larger wire, may be used at the sending station also. At the sending station, the coil is inserted between the spark gap and the antenna, or between the spark gap and the ground connection. Increase of inductance in either circuit increases the time of vibrations, which brings a corresponding increase of wavelength. The use of adjustable inductances in both the sending and the receiving circuits was apparently first suggested by Sir Oliver Lodge in a patent application of 1887, which is reviewed later in the present chapter. Certain other methods employed for adjusting both the sending station and the receiving station, and found to produce better results both for transmitting with large quantities of energy and for receiving with comparatively sharp resonance, make use of coupled circuits. The resonance relations in these coupled circuits has been the subject of much theoretical and experimental research. As introductory to the description of the coupled circuits, I shall recall to the reader the familiar and interesting experiments of Mr. Tesla and of Professor Thomson on the production of electric oscillations of high frequency and high potential. High-frequency transformers of Thomson and Tesla. The high-frequency transformer that was apparently independently developed by Mr. Hell, Nikola Tesla, and Professor Elihu Thomson about 1890 is shown in Figure 63. A primary coil P, consisting of 2 or 4 turns of heavy wire, is connected in series with a bank of Leyden jars C and a spark gap G. A secondary coil S, consisting of many hundreds of turns of wire wound in a single layer on a paper or vulcanite tube, is inserted axially within the primary. The bank of jars is connected by means of the leads WW' with the secondary of a Ruhmkorff coil, or better with the secondary of an alternating current step-up transformer. The Leyden jars are repeatedly charged by the Ruhmkorff coil or transformer at intervals of, say, 1/16th or 1/30th of a second. When the potential at each charge of the jars reaches a value high enough to spark across the gap G, the jars discharge with oscillations of extremely high frequency. A group of these oscillations occurs during each spark at the gap G. These high-frequency oscillations in the primary coil P act inductively on the secondary coil S, and on account of the extreme rapidity of change of current in the primary, the electromotive force induced in the secondary is very high, and produces a series of sparks between the terminals T1 and T2 of the secondary. It should be noted that the primary has a period of its own, and that the coil of wire S used as a secondary has also a period of its own. And in order to get the greatest spark at the secondary terminals, it is necessary to adjust the number of jars C, or else the number of turns of wire on either P or S, so that the condenser circuit and the secondary coil shall be in resonance with each other. By the use of apparatus of this character, Mr. E. Tesla has produced enormous sparks, 23 feet long and of great volume, graphically described as being accompanied by a roar like Niagara. The transformer PS is called a high-frequency transformer, an oscillation transformer, or an air core transformer, to distinguish it from an ordinary iron core transformer, such as is used with commercial alternating currents of slow frequency. Oscillation transformers, built on somewhat different lines from the one above described, have met with application to both the sending and the receiving circuits of electric wave telegraphy, and by the use of these transformers, a considerable advance has been made, both in the greater distances attained and in the diminished confusion of signals of different wavelengths. Two systems of coupled circuits. The form given to these coupled circuits is considerably varied in practice. There are, however, two important general types. These are represented in the accompanying figures, figure 64 and figure 65, and are called respectively the inductively coupled and the direct coupled types. The inductively coupled type. This type is shown in figure 64. In this system, the sending station, shown on the left, is seen to consist of a Tesla high-frequency apparatus with one secondary terminal connected to an antenna and the other secondary terminal connected to the ground. Power is supplied to the circuit by an alternating current transformer or a Ruhmkorff coil to which the wires W lead. The receiving station of this system, shown at the right in figure 64, has also an oscillation transformer PS' and is in principle like the sending station, except that the detector D with its accessories is usually put in place of the spark gap of the sending apparatus. The coils P' and S' and condenser C' used with the receiving apparatus generally have different inductances and capacity from those of the sending apparatus, and not being traversed by high potential currents, they are usually made more compact. In this inductively coupled system of circuits, oscillatory currents in the sending antenna are produced inductively by the oscillatory discharge of the condenser C through the primary coil P. These oscillatory currents in the sending antenna produce electric waves which travel away in all directions with the velocity of light, 186,000 miles per second. Arriving at the receiving station, these electric waves set up oscillations in the antenna circuit AP', E'. These currents through P' act inductively on S' and produce oscillatory currents in the detector circuit. The direct coupled type. Figure 65 shows the other form of coupled apparatus constituting the direct coupled system. This system employs autotransformers, that is to say, instead of having separate primary and secondary coils in the high-frequency transformer, the primary coil, P or P' at either station is a part of the secondary coil. At the sending station, at the left, the condenser discharges through some of the turns of the secondary, and the discharge acts inductively on the whole of the secondary. Likewise, at the receiving station, the oscillations in the antenna pass through a part P' of the secondary S' and act inductively on the whole of S'. Theory and experiment show that in principle the direct coupled circuits differ very little from the inductively coupled system. Introduction of coupled circuits into practice. Postponing for a time the direct discussion of the principles involved in the use of the coupled circuits, let us take up historically the matter of the introduction of these circuits into wireless telegraph practice. The examination of the question as to the priority of the different claimants to this improvement is fraught with considerable difficulty. Lodge and Marconi in England and Braun in Germany have clearly established dates of publication by patent applications. While examining the question of priority, I shall also give a brief description of the apparatus of these several inventors, so far as pertains to the form of circuits used. Sir Oliver Lodge's apparatus. On May 10, 1897, Professor Lodge filed a patent application in England for improvements in wireless telegraphy. The corresponding application in the United States was filed February 1, 1898. What he claims to be the most prominent feature of his invention is represented in figure 66. The emitter and receiver consist preferably of two large conical conductors called capacity areas, supported by poles. But horizontally placed conductors may also serve as his capacity areas, and one of these capacity areas, he says, may be the Earth. At the sending station, shown at the left, he joins the two capacity areas H and H' to polished knobs H² and H³. Between either capacity area and its knob, he places a syntonizing self-inductance coil. The object of this coil, Lodge says, is to prolong the electric oscillations occurring in the radiator, so as to constitute it a radiator of definite frequency or pitch, and obtain a succession of tone waves emitted, and thereby to render syntony in a receiver possible, because exactitude of response depends on the fact that the total number of oscillations in a suitably arranged circuit is very great. He provides also for varying the number of active turns of these coils for the purpose of varying the period of the circuits. After having described the ordinary way of charging the vanes of the emitter, by connecting them directly or through small spark gaps to the secondary of a Ruhmkorff coil, as Hertz and Righi had done, Lodge proposes also the use of Leyden jars in the manner shown in figure 67. In this diagram, the jars are shown at JJ. The inner coatings of the jars are connected to the secondary of a Ruhmkorff coil. The outer coatings of the jars are joined by an inductance coil of thin wire K. This coil is necessary in order that the jars may charge. When this discharge across the gap H² H³ occurs, sparks also appear across the gaps HH' and H', H'. This apparatus therefore shows the use of a Leyden jar circuit discharging into the antenna circuit, and if the coil K has a large inductance, as it seems to have from the fact that it is made of fairly thin wire, this sending arrangement may be looked upon as a special and very imperfect form of the direct coupled type of sending circuit of figure 65. It is imperfect in the use of the multiplicity of spark gaps, for if all the gaps except h squared h cubed had been closed, the coil K, which was put in as a charging bridge across the unnecessary gaps, could then have been omitted, and the apparatus would have been a very useful form of direct coupled emitter. While we are accustomed to the use of multiple gaps in replacement of a single gap, and while the multiple gap is in some constructions a distinct advantage over the single gap, still the introduction of one of the multiplicity of gaps directly into the antenna circuit is certainly an annulment of the chief advantage accruing from the coupled circuits. In the receiving apparatus, Lodge shows the use of an oscillation transformer. Reference is made to figure 68. His conical capacity areas or their equivalent are connected to the primary coil HH prime. About this, a secondary coil U is placed and is connected with the coherer C, a battery F, and the telegraphic receiving instrument T. The purpose of connecting the detector in a secondary circuit instead of directly in the antenna is, according to the patentee, to leave the resonator free to vibrate electrically without disturbance from attached wires. This is an excellent reason, but the receiving apparatus as shown in this diagram, which was taken from Lodge's patent specifications, has the fatal defect that no condenser is shown in the secondary circuit, and that the high-frequency oscillations have to go through the telegraphic instrument. Hence, apart from the suggestion of the use of a transformer in the receiving apparatus, we cannot consider this circuit of Lodge to be a clear disclosure of the inductively coupled receiving system. Later, Lodge and Muirhead, in a British specification filed December 8, 1897, partially remedied the above defect by the arrangement of circuits shown in figure 69. Between the two winged-shaped capacity areas AA, they inserted an inductance coil D and a large condenser C. About this condenser, a battery B and a telegraph instrument I are connected, and about both inductance and condenser is connected a coherer Co. With proper values of the inductance and capacity, this arrangement is a special case of the direct coupled receiving apparatus. These contrivances of Lodge and Muirhead seem not to have been developed by them experimentally to their natural completion, which would perhaps have led to one or the other of the types given in figures 64 and 65. They did come to one of these types much later, but only after Mr. Marconi and Professor Ferdinand Braun had published their descriptions of the coupled circuits and by various public demonstrations and polemics had shown the great advantage of the coupled circuits. Just a word as to Lodge's wing-shaped vanes at the transmitter and receiver. These are an enlarged oscillator and resonator, preserving the symmetry of Hertz's original apparatus. In practice, they have not been much used in this symmetric form, probably on account of the difficulty of giving to the apparatus sufficiently large dimensions when both vanes have to be supported vertically in an elevated position. In practice, Lodge and Muirhead early replaced the twin vane and sometimes also the top by the alternative, horizontally placed conductor, consisting of a sheet of wire netting. The spark gap, instead of being halfway between these conductors, is usually nearer the lower conductor, as shown in figure 70, with an inductance L added below the gap for preserving approximate electrical symmetry and for tuning. In addition to these various suggestions by Lodge in regard to the use of tuning coils and transformers in the circuits, and the maintenance by him of the possibilities of the ungrounded circuits, Professor Lodge, together with Messrs. Muirhead and Robinson, has also devised a new form of coherer. This is described in Chapter 16, the coupled circuits of Ferdinand Braun. Let us return to the matter of the coupled circuits. In a German patent, number 111578, applied for October 14, 1898, Professor Ferdinand Braun of Strasbourg in Germany describes a form of connection for an oscillator coupled with an air wire for spark telegraphy. He proposes to use in this invention, which is a sending apparatus, the waves which are produced by the discharge of Leyden jars in the presence of induction coils. The accompanying figures 71A, 71B, 71C, and 71D are taken from Braun's patent specifications. In 71A, F is a Leyden jar at the spark gap, P an inductance coil, and M the emitting wire. In 71B, the form of connection is so changed that a primary and a secondary coil are used so that in the circuit of the emitter M, a coil only is present. Figure 71C shows two Leyden jars connected one behind the other in so-called cascade connection, and figure 71D shows the same connection for the use of a transformed current. In examining these figures, it should be borne in mind that the two coils P and S, which for simplicity of drawing are shown side by side, are really wound one around the other so as to form an oscillation transformer. It should also be borne in mind while reading the specifications that Professor Braun means primarily to describe a method of connecting the Leyden jar circuit to what he calls the air wire circuit, and that the document does not purport to give a description of a complete sending apparatus. This is clear from his single claim at the end of his description. His claim is a form of connection of an oscillator coupled with an air wire for spark telegraphy, characterized by an oscillation circuit containing a Leyden jar and a spark gap, into which the air wire for sending out the waves is connected either directly or by means of a transformer, for the purpose of bringing by this means greater quantities of energy into action. His clear understanding of how this energy may be increased is evident in a paragraph of the specification which says, above all, it is necessary by using a spark gap with a very large capacity to increase capacity, by increase the energy in their potential amplitude by transformation as well by increase of capacity and by the use of powerful sources of electricity. The gain of energy by increasing the potential could not be attained with an emitter having the spark gap situated in the antenna, because there is a certain active spark potential which cannot be exceeded. This point is brought out in the specifications. However, neither in the German nor the corresponding American patent, filed February 6, 1899, does Professor Braun speak of the necessity of properly attuning the secondary circuit to the period of the condenser circuit, which is a prerequisite for attaining the high potential in the antenna circuit. And without this attuning of the secondary to the primary circuit, the large capacity of the primary condenser and the use of powerful sources of electricity would not give any advantage over the simple Marconi antenna. The first mention by Braun of the required tuning, so far as I have been able to find, is in a publication of the 5th of March, 1901, in the Physikalische Zeitschrift, Volume 2, page 373, and in a book by Braun entitled Drahtlose Telegraphie durch Wasser und Luft, published in 1901. In examining Braun's patent drawings, one may wish to know whether the antenna circuit is to be grounded or otherwise balanced by a capacity at the other end of the secondary. Nothing is said on this subject in the German patent, but in the corresponding American patent he says, with reference to figure 71D, that one end of the secondary coil of the transformer S is connected with the transmitting wire M, and the other end is shown prolonged and ending in an arrow to indicate that it may be prolonged by adding a suitable length of insulated wire or connected to some other capacity area. In his book of 1901, a corresponding prolongation or addition of capacity is indicated in his drawing of the direct coupled circuit, as is shown in figure 72. There is nothing in these early patents of Professor Braun relating to coupled circuits at the receiving station. The coupled receiving apparatus was undoubtedly invented by Marconi, based on his description of the inductively coupled apparatus. The date of publication of Braun is subsequent to that of Marconi, but the form used by Braun is substantially the same, Marconi's coupled circuits. Mr. Marconi, in an English patent applied for June 1, 1898, clearly sets forth the transformer arrangement for a receiving station. This is shown in figure 73, in which A leads to the antenna and E to earth. The coils JJ', which are represented as side by side, are the oscillation transformer and are really wound one around the other. The primary J' is connected to the antenna and the earth, while the secondary is in circuit with the coherer T and the condenser K'. A relay R and battery B are connected about the coherer through the choking coils CC'. This is, therefore, a clear presentation of the inductively connected receiving station. In 1900, Marconi was granted an English patent for an inductively coupled sending station also. This is shown in figure 74 and is of the typical form of figure 64, with, however, an added variable inductance G in the antenna. In the 1900 description of this apparatus, Mr. Marconi clearly points out the necessity of having the primary and the secondary circuits at the sending station and the corresponding circuits at the receiving station adjusted to resonance with one another. He says, the capacity and self-induction of the four circuits, that is the primary and secondary circuits at the transmitting station, and the primary and secondary circuits at any one of the receiving stations in a communicating system, are each and all to be so independently adjusted as to make the product of the self-induction multiplied by the capacity the same in each case or multiples of each other. That is to say, the electrical time periods of the four circuits are to be the same or octaves of each other. The advantages of the coupled circuit at the sending station, according to Signor Marconi, arise in the approximately closed circuit of the primary being a good conserver and the open circuit of the secondary being a good radiator of wave energy. The variable inductance G in figure 74, placed in the antenna of the sending circuit, and a corresponding coil at the receiving station were used to aid in this process of tuning. A sending and a receiving station devised by Mr. Marconi for sending or receiving two messages at once with the use of a single antenna are shown in figure 75 and figure 76. This was successfully employed and exhibited by Marconi in the autumn of 1900. Two operators at the two keys K and K of the sending station made the signals. The two condenser circuits, having different values of capacity and self-induction, were independently charged and discharged with different periods of oscillation. These two periods were both impressed on the antenna through circuits which, by means of the antenna inductances D and D', were made to resonate with the respective condenser periods. At the receiving station, figure 76, the waves constituting the double message acted on the receiving antenna. The waves of the shorter period induced oscillations through the antenna and through the right-hand primary to the Earth, while the oscillations of longer period passed through the circuit to the left, which contained the greater inductance in the antenna circuit. The two periodic disturbances, thus separated, act inductively on their properly tuned coherer circuits and give up the two messages without confusion to the two receiving instruments. This duplex wireless telegraphy can be carried on only provided the wavelengths of the two sending stations are not too nearly equal. Some very notable achievements were made by Mr. Marconi with these resonant circuits in 1901 and 1902. A sending station of great power was completed at Poldhu in Cornwall, England in 1901. In December of that year, signals were reported to have been sent across the Atlantic Ocean from Poldhu to Cape Race near St. John's in Newfoundland. The signals, which consisted of the letter S repeated at stated intervals, were said to have been clearly received at Cape Race by means of a receiving antenna consisting of a copper wire 400 feet long supported by a kite. The detector employed in the transatlantic experiments was an instrument known as the Italian Navy coherer and consisted of a globule of mercury between iron terminals in a glass tube. This form of detector is self-restoring, and with it a telephone receiver in series with a battery is used in the local circuit in place of the ordinary telegraph relay. In March 1902, messages sent out from Poldhu were received by the Marconi apparatus on board the steamer Philadelphia when the steamer was 1,550 miles or 2,400 kilometers from the sending station. In December of the same year, Marconi announced the transmission of 3 entire messages from Glace Bay, Nova Scotia, to Poldhu in England, a distance of 2,300 miles. On January 19, 1903, the powerful Marconi station at Wellfleet, Cape Cod, Massachusetts, transmitted to Poldhu, England, the following message from the President of the United States to the King of England, His Majesty Edward VII, London, England. In taking advantage of the wonderful triumph of scientific research and ingenuity which has been achieved in perfecting a system of wireless telegraphy, I extend on behalf of the American people most cordial greetings and good wishes to you and to all the people of the British Empire. Theodore Roosevelt. Wellfleet, Massachusetts, January 19, 1903. This message, though intended to be relayed at Cape Race, was received, according to reports issued by the Marconi Company, direct at the Poldhu station in England. Chapter 14. Nature of the oscillation. The grounding of circuits. In the 2 preceding chapters devoted to a period of invention and rapid development of wireless telegraphy, several important facts have been introduced with only casual examination. Among the questions there raised, the most interesting is perhaps the question of the role played by the Earth. This question has 2 aspects. First, it has been seen that both grounded and ungrounded oscillators have been employed. What is the relation between these 2 forms of oscillator, and what effect has the ground connection on the nature of the vibration? Second, it has been apparent from the great distances attained in the transmission of messages entirely across the Atlantic Ocean that the electric waves are not lost to the receiver by reason of the curvature of the Earth, even when the 2 stations are separated by a distance that is a considerable fraction of the Earth's whole circumference. How is it that the electric waves are propagated from one station to the other, and how does the Earth contribute to the process? These 2 questions, dealing with the nature of the vibration and the manner of the propagation of the waves, will be considered respectively in this chapter and in the next chapter. As introductory, we shall need first to consider the oscillations occurring in a simple ungrounded Hertz oscillator. Current and potential in a Hertz oscillator. Suppose the Hertz oscillator to consist of 2 metallic rods or wires with a spark gap between, and suppose the 2 halves of the oscillator to be charged, one positive and the other negative, as shown in the first diagram, A of figure 77, in which the shaded area attached to the upper half of the oscillator is taken to indicate positive electricity, while the unshaded area attached to the lower rod indicates negative electricity. These areas are made fractional so that there is at the outset a definite quantity of electricity distributed uniformly throughout the upper rod and an equal quantity of negative electricity distributed uniformly throughout the lower rod. If the electrostatic capacity per unit of length of the rods is uniform throughout both rods, which is approximately true, when the rods are not too short, the potential of the conductor at any point of its length will be proportional to the charge, so that the shaded area representing a distribution of positive charge may also be looked upon as showing the distribution of positive potential, while the unshaded area represents negative potential. Thus, in the condition depicted in diagram A, there is a uniform positive potential over the top rod and a corresponding negative potential over the bottom rod. This is before the spark begins. Suppose now the spark to start between the rods. The gap between the rods becomes conductive, and a current begins to flow between the rods. There is a flow of positive electricity from the top rod and a flow of negative electricity from the bottom rod. The electricity to flow first across the gap is that in the neighborhood of the spark gap, because it is there that the potential gradient is greatest. After a short time, 1/4 the period of a complete oscillation, the condition of the charge and likewise the potential of the rod will be that condition represented in diagram B, in which 1/2 of the positive electricity has gone into the lower rod and half the negative electricity has gone into the upper rod, giving both rods equal quantities of positive and negative electricity so that both rods are neutral. Why then does not the action cease? In order to be able to see why the action does not cease when the charge has become neutral throughout the oscillator, we must take into consideration the current in the conductor as well as the charge. The second row of diagrams of figure 77 represents the current at the epochs corresponding to the potential representations of the first row. At the beginning, the potential or charge distribution is shown by diagram A of the top row. At the same time, no current is flowing, which fact is represented by the inactive oscillator shown at a prime of the second row. The current is now supposed to begin. It cannot spring to its final value at once because the increase of the current builds up a magnetic field surrounding the oscillator, and this growing magnetic field produces an electromotive force in the conductor opposing the growth of the current. Time is thus required for the current to become established. At a time equal to 1/4 the period of complete oscillation, time t equals t/4, the current has grown to its maximum value, which is represented at B prime. The shading to the right of the conductor is meant to represent the magnitude of the current at each point of the conductor, though the current is along the conductor and not perpendicular to it, as the shading is. It is interesting to note that the current is not uniform throughout the length of the conductor. The current is greatest near the middle of the conductor and is 0 at each end. The reason that it is greatest at the middle is that the current flowing out from the center toward either end decreases by reason of the charge that it leaves along the conductor en route. At the very end of the conductor, the current is 0 because no electricity flows out beyond the end and none flows in from beyond the end. We have thus in the conductor a distribution of current like that of B prime, large in the middle and 0 at both ends. Thus, at the time t equals t/4, the conductor is in a neutral condition with respect to charge, but is being traversed by a current in a downward direction. This current is a maximum with respect to time, and from this instant, the positive electricity in the lower rod begins to pile up at the gap, while the positive electricity in the upper rod flows out beyond the end. The current continues to flow downward, though decreasing, because any diminution of the current diminishes the surrounding magnetic field and gives an electromotive force tending to preserve the current. The current thus continues to pile up a positive charge on the lower rod, in spite of the fact that this piled up charge is exerting a restoring force. Presently, however, this restoring force, which has gone on increasing, brings the current to a stop. Then, when there is no current, there is no magnetic field, and the accumulated positive electricity on the lower rod starts the current upward. This reversal of the current occurs at a time t equals t/2, and the condition of the charge and current is represented at C and C prime. The upward current continues to flow and produces successively the conditions D and D prime at time t equals 3t/4 and E and E prime at time t equals t. In the last named state, the upper rod is entirely positive, while the lower rod is entirely negative. This resembles the initial state of the rod, but is not identical with it because the initial state was brought about by an extraneous slow charging source, Holt's machine or Ruhmkorff coil, instead of by the very rapid surging that is going on in the oscillator when it is oscillating with its own natural period. From the condition of initial uniform distribution, we have followed the charge and current by rather large stages of 1/4 of a period each through a single oscillation. The charge on the oscillator will continue to oscillate, going through the successive steps several times, the accumulation of electricity becoming less and less at each oscillation until the spark extinguishes. Nodes and loops of potential and current. From the preceding discussion, it is apparent that the two ends of the Hertz oscillator undergo maximum fluctuations of potential and are therefore loops of potential. The middle of the conductor during the oscillation has no accumulation of charge on it. The potential is therefore fixed and therefore is a node of potential. On the other hand, the two ends of the conductor are nodes of current because no current flows through them, while the middle of the conductor is a loop of current because the current there has its maximum value. Experiments on the distribution of current in an ungrounded Hertz oscillator. In the preceding discussion, there was given a theoretical examination of the nature of the potential and the current distribution occurring in a Hertz oscillator. I have recently made a simple experiment that approximately confirms the deductions there given in regard to the current. The principle of the experiment and a description of the oscillator. The principle of the experiment is illustrated in figure 78. Instead of making a breach at various points in the oscillator and inserting therein an instrument for determining the current, this current at different points in the oscillator was studied by means of its inductive action on a small neighboring circuit WM placed successively at different positions along the oscillator, as indicated by the dotted squares in figure 78. The spark gap of the oscillator is shown at G. The two conductors of the oscillator OO were each a wire 1 millimeter in diameter and 9 meters long, supported horizontally 1 meter above the wooden floor of a long room in the third story of the laboratory. The oscillating system was thus at a height of about 10 meters above the surface of the Earth, and was probably very little disturbed by the capacity of the Earth. The oscillator was supported by 3 insulating stands, one at the spark gap and one at each end of the wire. The central stand for supporting the spark gap carried also a storage battery and a small Ruhmkorff coil for charging the oscillator. The exploring circuit. An enlarged view of the apparatus showing details of the exploring circuit by which the measurements were made is given in figure 79. This circuit, shown at the left in the oscillator, consists of a square loop of heavy copper wire L, 30 centimeters on a side, and having in series with it a variable condenser C and a high-frequency current reading instrument at I. I shall now describe the instrument I and the condenser C. Description of the instrument. The instrument at I, as shown in figure 80, consists of a disc of silver, suspended by a fine fiber of spun quartz, so as to hang near a small coil of a few turns of wire with which the disc made an angle of 45 degrees. The disc is at M, and the coil, which in this experiment consisted of 5 turns of wire wound on a vulcanite tube, is shown at C, figure 80. The two ends of the coil are connected to binding posts by which the coil is put into the circuit. The front of the disc carries a small mirror, enabling the deflections of the disc to be measured by means of a telescope and scale, such as is used with delicate galvanometers. The mounting of the instrument is also shown in figure 80. The disc is suspended in the vertical vulcanite tube, which is mounted on leveling screws. The support of the coil is inserted in the side of the vertical tube and is arranged to be moved in and out by a micrometer screw. This delicate motion of the coil in or out brings the coil nearer to or farther from the suspended silver disc so as to vary the sensitiveness of the instrument to make it suitable for measuring small or large oscillating currents. The action of the instrument, which we shall call a high-frequency dynamometer, is as follows. Oscillations in the coil induce oscillations in the disc. Between these two sets of oscillations, there is a force which causes the disc to tend to set itself at right angles to the coil. The deflections of the dynamometer are proportional to the square of the current through it. The variable condenser. Returning to figure 79, the loop L contains, besides the high-frequency dynamometer I, a variable condenser C. This condenser is of a form much used in wireless telegraphic apparatus and is described by Korda in German patent number 74477, issued December 13, 1893. It consists of 2 sets of semicircular plates, one set F being connected together and fixed in position, and the other set H being also connected together and capable of rotation about a central axis. By rotating the plates H so as to bring a greater or less area of the 2 sets of plates into interlapping position, the capacity of the condenser can be varied. The position of the plates H with respect to F can be read on a scale attached to the top plate of H and passing under a fixed pointer. A photograph of a condenser of this character with capacity somewhat larger than that of the condenser employed in these experiments is shown in figure 81. Large current at resonance. Variations of the capacity of C varies the natural period of oscillation of the condenser circuit, and when this period is made equal to that of the Hertz oscillator OGO, a maximum deflection of the instrument I is obtained under the action of the oscillation. The resonant condenser circuit, when calibrated in terms of wavelength, is a form of wave meter. How this calibration is effected will be shown later. Exploration of current distribution. Since the wave meter in this form, on account of the instrument I, is not conveniently movable, it was necessary to move the oscillator in order to explore the distribution of current in the oscillator. The oscillator, with its exciting induction coil and storage battery, was moved lengthwise, keeping it always the same distance from the wave meter by means of the vulcanite guides DD of figure 79. Readings of the dynamometer were taken for various positions of the oscillator with respect to the wave meter. This was equivalent to moving the wave meter along the oscillator, and the readings of the dynamometer were proportional to the square of the current in the wave meter, and therefore proportional to the square of the current at different points of the oscillator, because the induced current, keeping everything else the same, is proportional to the inducing current. The results obtained for the distribution of the current in the oscillator are plotted in figure 82. The curve of figure 82 shows that the current in the oscillator is greatest near the gap and falls off to 0 at the ends of the oscillator in a manner not very different from that predicted by the theoretical drawings of figure 77. The maximum is located in the middle and a node at each end of the oscillator. Experiments on the wavelength of the ungrounded Hertz oscillator. Wavelength of the Hertz oscillator. Having investigated the distribution of current and potential in an ungrounded oscillator, let us next inquire what is the wavelength of the electric wave emitted by such an oscillator. With an oscillator of 2 parallel wires near together, as shown in figure 83, the length of the wave is very approximately 4 times the length of one of the wires, GBC. If now we take the two parallel wires, separate them, and extend them out oppositely to each other from the gap so as to form the Hertz oscillator, does the wavelength remain the same? Namely, lambda equals 4L, where lambda is the wavelength and L is the length of the half oscillator. Some theoretical writers, for example Abraham, say that it does remain equal to 4L, while MacDonald has computed in this case to be 5.06 times L. Recently, Messrs. Webb and Woodman, for very short oscillators, with a half-length L between 1 and 5 centimeters, have obtained experimentally the relation lambda equals 4.8 Ls. For oscillators of half-length between 1 and 3 meters, F. Conrad has obtained the values presented in the accompanying table, with the average relation lambda equals 4.24 Ls. Conrad's table for relation of lambda to L. Half-length of oscillator in meters, 1.0, wavelength 4.20 meters, ratio 4.20, 1.92, wavelength 8.40 meters, ratio 4.37, 2.30, wavelength 10.0 meters, ratio 4.35, 3.1 fein, wavelength 13.2 meters, ratio 4.19. Average equals 4.24. The experiments of Conrad and those of Messrs. Webb and Woodman both give evidence of being very careful experiments, and we must therefore conclude that the ratio lambda over L for very short oscillators is greater than for the long oscillator. We are primarily interested in the long oscillators, and in order to extend the experimental records to the case of longer oscillators than those studied by Conrad, I have made a series of measurements with the apparatus of figures 78, 79, 80. Calibration of the wave meter. The wave meter was calibrated for various adjustments of the condenser C by setting it to resonance with various lengths of the two parallel wires of figure 83, as had been previously done by Drude. With the wave meter calibrated to read directly in wavelengths, the parallel calibrating wires were removed, and the Hertz oscillator, consisting of two oppositely extending wires of various lengths, 1 millimeter in diameter, was brought up near the wave meter, and the wavelength produced by the oscillator was determined. The results obtained are given in the following table. The average of the results obtained by the author for the ratio of lambda to L, namely lambda over L equals 4.19, for wavelengths between 17 and 63 meters, is a little less than the corresponding ratio 4.24 obtained by Conrad for wavelengths between 4 and 13 meters. The difference is only 1%. From these results, we may conclude that the wavelength produced by a Hertz rectilinear oscillator is very approximately 4.20 times the length of one limb of the oscillator, provided this limb is greater than 1 meter long and of comparatively small diameter. Let us next see how the vibration of a conductor is modified when one end is connected to earth. On grounded circuits. Grounded circuits. Image theory. Suppose now the lower limb of a vertical Hertz oscillator to be cut away close up to the spark gap and be replaced by a connection to earth. According to electrical theories, if the earth were a perfect conductor, the electrical wavelength of the earthed system would be the same as that of the Hertz oscillator, the earth merely taking the place of the other half of the Hertz oscillator. The earthed system, which is a simple Marconi emitter, would have the same distribution of current and potential in the antenna as the upper half of the Hertz oscillator had before removing the lower limb. In order to examine this theory, let us confine our attention in the beginning to a receiving station, and suppose that we have there simply an ungrounded rectilinear conductor isolated in space and placed parallel to the electric force of the incoming waves. Let the length of this straight line conductor be so chosen that its natural period of electric oscillation is equal to the period of the waves. The distribution of current in the conductor would resemble that shown in figure 82. If we could introduce a current reading detector into the circuit without disturbing the conditions, this instrument would give a maximum reading when placed at the center of the receiving conductor, and its reading would be 0 when the instrument is placed at the ends. Suppose with such an instrument in the circuit we should cut away the lower half of the conductor. The reading would become 0 because there would be no capacity out beyond the instrument into which the current could flow. If now a capacity is attached to the instrument in the place of the removed conductor, some current would flow between the straight wire and the capacity and register in the instrument. If the capacity attached were very large, for example the earth, the point of zero fluctuation of potential would again be brought near the instrument, because a large fluctuation of potential cannot occur in a very large capacity under the action of the currents with which we are concerned. We should therefore have the same current as when the conductor was made up of two parts symmetrical about the instrument. In actual systems, the grounding may be imperfect. In that case, the symmetrical image would give only approximately an equivalent system. I have made some experiments to test this image theory of the action of the ground connection. The experiments consisted in comparing resonance curves taken with various forms of grounded circuits with the corresponding resonance curves taken with an image circuit in the place of the ground. Two of these experiments are here briefly described. Experiments to test image theory of the ground. Experiment 1. The aerial circuit and its image tuned by variable inductances. In testing the image theory of the action of the ground at the receiving station, the form of circuit shown in figure 84 was employed. The high-frequency dynamometer described previously was used for detecting and measuring the minute oscillating currents at the receiving station and was placed at I in series with a variable inductance and a vertical antenna 23.2 meters long. This aerial system, by means of a switch at S, could be connected to the ground B, or the ground could be thrown on replaced by metallic parts duplicating the aerial system. The duplicate was, however, not an exact theoretical image of the aerial system, because the second antenna had to run off horizontally instead of straight down. The horizontal wire was made equal in length to the vertical antenna, 23.2 meters, and was supported about 1 meter from the ground by cords attached to posts. In series with the horizontal wire was a variable inductance L prime, duplicating the tuning coil L, and a small coil I prime of fine wire, duplicating the coil of the receiving instrument. Curves giving the results of the experiment are shown in figure 85. For curve G, the ground circuit was used, and deflections of the receiving instrument were taken for various values of the inductance of the tuning coil L. The deflections are plotted against values of L. The switch S was then thrown so as to connect the receiving circuit to the horizontal system instead of to the ground. With this arrangement, the curve H was obtained. In taking this curve, the tuning coil L and its image L prime were kept identical and varied together. The curve H therefore shows the deflections of the receiving instrument plotted against the common values of L and L prime. Discussion of results in experiment 1. The two curves G and H of figure 85 are seen to have their maxima for the same value of inductance. That is, a given value of inductance, 2.1 times 10 to the negative fifth henries, gives a maximum deflection in the case of the grounded circuit. To obtain a maximum with the duplicated system, the same inductance 2.1 times 10 to the negative fifth henries must be used in both the vertical circuit and in its horizontal duplicate. The result is a confirmation of the image theory of the grounded circuit. The earthing of the circuit gives it the same period of vibration as the duplication of the aerial system gives. It is interesting to note that the deflection, meaning the current squared, is about 20% larger with the grounded system than with the ungrounded system. This may be accounted for by supposing a higher resistance in the horizontal duplicate system than in the simply earthed circuit. Experiment 2. Quarter wave ground. What was perhaps a more interesting experiment, confirmatory of the image theory of the ground, was made by replacing the ground by a horizontal wire of which the length could be varied. The relative amounts of energy received, deflections for different lengths of the horizontal wire are shown in the curve A of figure 86. Resonance was obtained when this wire had the length of 38 meters, which was very close to 1/4 the wavelength, 153 meters. The ground gives the system the same period as an added quarter wave wire gives the system. Curve B, obtained with different conditions, leads to the same results. Conclusion from the experiments. These experiments 1 and 2 show that the effect of the ground, so far as concerns the vibration in the antenna, is to introduce into the circuit at the ground a point of zero fluctuation of potential, an effect that can also be obtained with an artificial ground consisting of a symmetrical duplicate of the aerial system, or consisting of a horizontal wire not far from the Earth and of length equal to 1/4 of the wavelength to be received. Professor Ferdinand Braun, at a date earlier than that of my experiments, has suggested the use of horizontal wire in replacement of the ground, and also the use of a capacity consisting of a large cylindrical conductor in the place of the ground. He has not, however, so far as I know, published any quantitative results on the subject.